Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. In this video, we are going to discuss the relationship between CPM and CVM. CPM is a constant molar heat constant for constant pressure, and CVM is the molar heat molar heat capacity for the constant volume, and also both have constant mass. In the previous lesson, we have discussed the heat supplied to increase the temperature of n moles of gas by 1 Kelvin at constant pressure delta Q is given by n CPM delta theta, and whereas the heat supplied to increase the temperature of n moles of gas by 1 Kelvin at constant volume is given by delta Q equals to n CVM delta theta. Okay, we are going to discuss for changes in the 1 mole of an ideal gas. Okay, the figure below shows the initial states and the final state of 1 mole of ideal gas for two cases. For the first case, the initial state, let's say pressure P, volume is V and temperature is T. And final state, the pressure is P plus delta P, volume constant V, and temperature T plus delta T. Okay, this is for the first case. For second case, initial with the same pressure, volume, and temperature for the case 1. But the final case, we make P constant, pressure constant, and the volume increase by delta V and the temperature increase by delta T. So for both case 1 and case 2, the temperature increase by delta T. Okay, for the first case, we use first law of thermodynamics, delta Q equals to delta U plus work. For the work done by the gas, because of the volume has no change, so therefore work done is 0. And for delta Q, this is constant volume, so we choose delta Q equals to n CVM delta T, where n is 1 mole, so therefore the delta Q equals to CVM delta T. So we substitute into the first law of thermodynamics for work and delta Q, so we get delta U, change in internal energy. So the change in internal energy is equals to CVM delta T. Okay, this is for the first case, we get internal energy equals to CVM delta T. So let's call this equation as equation 1. So we keep this for a while, and we are going to discuss for second case. For the second case, we still use first law of thermodynamics. So for the delta Q, because this is constant pressure, so we use the heat capacity equals to n CPM delta T, and n is 1 mole, so therefore delta Q equals to CPM delta T, molar heat capacity at constant pressure. And the work done, the pressure is constant, so we can use work equals to P delta V. So P is constant because we have final and initial state. So for the initial state, for work equals to for the PV equals to nRT, relationship between we use equation PV equals to nRT, and for 1 mole, so we substitute P and V here into here, and RT. This is initial state. For final state, we substitute P, the same P, pressure constant, and volume becomes V plus delta V. R is a constant, and temperature becomes T plus delta T, and we expand the bracket here, P times Vm plus P times delta V equals to R times T plus R times delta T. So this is for final state for case 2. So we have two equations here, so we use simultaneous equation to solve to get work done. P delta V here, the work is P delta V. So for equation 1 and 2, we use simultaneous equation 2 minus 1, or substitute 1 into 2 also can. So let's say we use 2 minus 1, So PVM can be cancelled out, RT also can be cancelled out. So we get P delta V equals to R delta T. And this is work done. So we substitute into the above, we get work done R delta T. And this work is can be substituted into the first law of thermodynamics just now. Work equals to R delta T. Okay, now for delta U, we use the first case. For the first case, we get delta U, change in internal energy, equals to CVM delta T. Okay, for the first case. Okay, now we substitute everything into the first law of thermodynamics here. We can get the relationship between CVM and CPM. So delta Q is CPM delta T, delta U is CVM delta T, and the work done is R delta T. Combine all the equations, okay, into the first law of thermodynamics. So we can cancel out delta T, and therefore the CPM equals to CVM plus R, and we get CPM minus CVM equals to R. CVM bring to the right side become minus. So this is the relationship between the molar heat capacity at constant pressure and at constant volume with R. Okay, from this relationship, CPM minus CVM equals to R. R is always positive, so therefore CPM is always larger than CVM because we get positive value. So larger value minus lowest value, larger value minus lower value, we get positive value. So it is understood that from this relationship, CPM is always larger than CVM. Okay, if we plot the graph P against V for the two case, okay, the first case, case 1, PVT, V constant, okay, at final and initial. So at initial, the V constant, so the graph must be a straight line. Where the X to Y changes, the initial is P, final will be P plus delta P, and the volume for both initial and final still give the reading V. That's why it's a straight line graph, vertical straight line graph. And for the second case, pressure is constant, so it will be the horizontal line graph. Okay, P at final and initial and final is constant. Okay, given by the reading at the y axis, and at the x axis, V increased by delta V. And for the temperature, for the first isotherm, temperature is T, and this line is called isotherm. For first initial isotherm will give the temperature T, and the final isotherm will give the temperature increased by delta T. Okay, for all the points along the isotherm line has the same temperature T plus delta T. Okay, and for the first isotherm, all the line here at any point P and V value will give the same temperature T. Okay, we try this example. Given the molar heat capacity for the gas at constant volume, CVM is 30.97 joule per mole per Kelvin, and the temperature of the gas at X is 410 Kelvin. And the PV graph here is for the 2 moles of ideal gas in a container, and that means they have same mass. Okay, find the amount of work done by the gas, calculate the temperature of the gas at Y, determine the amount of heat supplied to the gas, and calculate the change in internal energy of the gas, and lastly deduce the value of molar heat capacity CPM for the gas at constant pressure. So we do a question first. Find the amount of work done by the gas. Because the work done is a constant in the constant volume, okay, V0 here, the reading is at certain value V for final and initial, so therefore there is no change in the volume, so therefore the work done is 0. Okay, for question B, calculate the temperature of the gas at Y. So we use pressure gas law where volume is constant. V1 and V2 is constant. So we use P1 per T1 equals to P2 per T2. So substitute the P1 20 kilopascal and P2 50 kilopascal, and the kilo can be cancelled out, leaving 20 and 50. And temperature, initial temperature is given 400 Kelvin. Final temperature is what we are going to find. And cross multiply, we get T2 equals to 50 per 20 times 410. So we get temperature 1025 Kelvin. Okay, next, determine the amount of heat supplied to the gas. So to determine the heat supplied to the gas, so we use molar heat capacity for constant volume. So where the heat supplied is given by N CVM delta T. So we substitute N 2 moles, CVM is 30.97 joule per mole per Kelvin, and temperature difference is 1025 minus 410 joule. So we get heat supply is 38,093.1 joule. So the heat supply is positive, and we get the value here is positive. Okay, next we are going to calculate the change in internal energy of the gas. To calculate the change in internal energy of the gas, we use first law of thermodynamics. Delta Q equals to delta U plus work done. So from question A, work done is 0, and the delta Q is 38,093.1 joule. So we substitute into the equation here, we get internal energy. So internal energy is the same as the heat supplied because the work done is 0. So that means that internal energy is also 38,093.1 joule. Okay, lastly for the question E, deduce the value of the molar heat capacity CPM for the gas at constant pressure. So we use the relationship between molar heat capacity at constant pressure and molar heat capacity at constant volume, where CPM minus CVM equals to R. So CPM is equals to R plus CVM. So we bring the minus CVM into the right side, become plus CVM. We substitute the R 8.31 plus CVM is 30.97 to the equation. So we get 39.28 joule per mole per Kelvin. So this is the CPM value, molar heat capacity at constant pressure and constant mass. Okay, that's all for the video, and thank you for watching.